You optimize the math in your GPU program, each operation becomes faster, but the complete application barely improves. Then you open a profiler and the timeline looks like a picket fence. Tiny kernel, small gap, another tiny kernel, another gap. The GPU is powerful, but we keep feeding it work in very small pieces. Here is the surprising part. Sometimes faster GPU code does not begin with doing fewer calculations. It begins with launching fewer kernels and moving less intermediate data. Let us see why that works when it fails and how you can decide with measurements instead of guesses. First, what are we launching? A CUDA kernel is a function that runs across many GPU threads. Your CPU side program configures a grid, provides arguments and submits the kernel to a CUDA stream. The launch is asynchronous. The CPU call can return before the GPU finishes the work. But asynchronous does not mean free. The runtime processes the launch, the work may wait in a queue, and the GPU executes it and site. System separates this into API time, queue time, and kernel time. For a large kernel, launch cost may be irrelevant. For hundreds of tiny dependent kernels, it can become visible as CPU activity, GPU gaps, or too little useful work per launch. There is no universal launch overhead number that you should memorize. Look at your real profile. Is dispatch a meaningful fraction of this workload? Now let us use NVIDIA's simple example, sum of absolute x. We take the absolute value of every array element, then add those values together. The obvious implementation uses two kernels. Kernel 1 reads x and writes the absolute values into a temporary array. Kernel 2 reads that temporary array and reduces it to one result. The two launches matter, but look at the data path as well. The first kernel reads and writes every element. The second reads the temporary. Again, that is 3 large passes through device global memory for an array that exists only to connect two operations. This is not a CPU to GPU copy. The data remains on the GPU. The waste is the round trip through device memory between kernels. If the arithmetic is cheap and memory bandwidth is already busy, that extra write and read can dominate the runtime. Kernel fusion combines compatible operations so that an intermediate value can be consumed before it becomes a full global memory buffer. In the fused version, each thread loads X and computes its absolute value immediately. It can stay in a register and enter a local partial sum. Threads then cooperate on a block level reduction using shared memory before contributing to the final result. Now we have one main launch and no per element temporary array. NVIDIA measured a 1 GB input on a GeForce RTX 4090. The naive path moved about 3 GB and took 3.51 milliseconds. Manual fusion moved about 1 GB and took 1.8 milliseconds. That is close to a 3 times speed up in this particular test. But notice what did not change much: effective memory bandwidth. Both versions were already near the same bandwidth. The fused kernel was faster because it asked memory to do less work. We removed traffic and one launch. You can reach that result in different ways. With manual CUDA fusion, you write the combined kernel yourself. You gain control, but also own its testing, tuning, and maintenance. A compiler can fuse operations for you. In NVIDIA's torch.compile example, the compiler moves the absolute value operation inside the reduction. The last temporary disappears, although a small second stage kernel remains. That detail is important. Fusion does not always mean exactly one kernel. The real target is unnecessary work, not the smallest possible launch count. Compiler fusion can be less predictable. A new shape, data type, guard, or code path can change the graph. In torch.compile, some changes can trigger recompilation, so include that cost in warm-up and latency measurements. CUDA Graphs solve a related but different problem. A graph packages repeated operations for lower host submission overhead. Its kernels remain separate, so full intermediate buffers do not disappear automatically. So if launch submission is the problem, a graph may help. If global memory intermediates are the problem, kernel body fusion may help. Sometimes you use both. At this point, you might ask, why not fuse everything? Because one large kernel inherits the resources and constraints of everything you combine. More operations keep more values alive and can increase register pressure. Registers are limited across active threads. If a block needs too many registers or too much shared memory, fewer blocks can stay resident, reducing the GPU's ability to hide latency. Higher occupancy is not automatically better, but unexpectedly low occupancy is a warning. Register spills into local memory can also restore traffic that fusion was meant to remove. There are semantic limits too. Independent kernels might overlap in separate streams, while fusion can remove that concurrency. Some algorithms need a real grid-wide boundary. Blocks inside an ordinary kernel cannot always coordinate like two ordered launches. A giant kernel may also gain branches or become harder to tune. The goal is the right fusion boundary, not maximum fusion. Here is the workflow I would use with you. Start in Inside Systems, find a repeated chain of short dependent kernels and inspect its API activity, gaps and memory operations. Queue time alone is not bad, it may mean the GPU is busy. We want avoidable launch work or idle time tied to the chain. Next, state one precise hypothesis. These two operations create a full temporary buffer, and fusing them should remove one launch, one write, and one read. Build only that change, then return to Inside Systems and confirm that the timeline changed as expected. After that, inspect the fused kernel in Inside Compute. Did memory traffic fall? Did registers, spills, occupancy, or kernel duration get worse? Benchmark realistic sizes, warm up compiler-generated paths, separate compilation from steady-state execution, and verify the numerical result because reduction order can change floating point rounding. Finally, measure the complete application. A prettier kernel profile is not useful if end-to-end latency becomes worse somewhere else. So, faster GPU code can mean launching fewer kernels, but kernel count is only the visible clue. The real opportunity is a measured producer-consumer chain where launch work is significant or a temporary array is wasting global memory bandwidth. Fuse that boundary, keep the intermediate close to the threads when the algorithm permits, and then check the new resource footprint. If the kernels should stay separate, test CUDA Graphs. If fusion increases registers, spills, or synchronization complexity, step back. Do not optimize for the fewest boxes on a profiler timeline. Optimize for less total work on a verified workload. If this helped you understand what a GPU profiler is really showing, share it with someone learning CUDA and subscribe for more engineering mechanisms explained visually.